Good morning, everyone. Today we are going to continue on this lecture with the topic of cryptographic algorithms, and later on we will be discussing artificial intelligence algorithms. First of all, I apologize for my voice due to the medical procedures. My voice is having a bit of a problem. I also have a very severe pain in my throat, so I really apologize. Okay, so let's start with this lecture. In this lecture, we will continue from the last time. We talk about cryptographic algorithms, and last time I explained what is a cryptographic algorithm, and then I show you the cryptographic algorithm is an algorithm that transforms a plain text into a ciphertext. The cryptographic algorithm basically provides a process called encryption. Plain text letters such as the word hello, and then the ciphertext can be anything. Maybe it is something that human can even read. For example, and then every time we create an encryption algorithm, usually we will have a decryption algorithm that would reverse the ciphertext back into the plain text. So this is a process called cryptographic algorithm. Usually, a cryptographic algorithm are two ways. For example, with the Caesar cipher, our encryption algorithm is that in order to send a secret message. In the past, um, when someone like King Julius Caesar, for example, he would like to send a secret message to someone, like for military purpose or for some personal purpose, and he wants no one to know about it except the receiver. So he said that any alphabet that is used will be shifted by some number k, for example. So in this case, he wants the value k to be 3. And then each alphabet, for example, hello, if we look at it in the alphabet table, you will see that the position H is 8 will be shifted by 3 positions. And then if it goes beyond the position of letter Z, then the information will be wrapped around going back to the beginning. That's why we need the mod function. The mod function is used to find the remainder between the number and this number 26. And so finally, we will get the ciphertext letter. So in this case, the word hello is now encrypted to become the word KHOOR. And since this letter is not in the dictionary, so basically no one except the final recipient would be able to understand this. Mm. There are three types of cryptographic algorithm. In the previous example, I show you that a cryptographic algorithm consists of mainly two things in terms of the algorithm. We call this the protocol because cryptography is highly related to communication and networking. So the terms that we use is called protocol, or in a sense, it is a language. And this language consists of one, the semantic, two, the syntax, and finally, the timing or synchronization. The semantic, in this case, represent the input set and its definition. In the Caesar cipher example, the input set are alphabets. It can be alphabets. It can be words. Can be numbers. Can be anything that we want to be used as our input. And these are called plain text, things that humans understand. And then there are a set of output. Which can be anything, just like this. Could be alphabets, can be words, can be numbers. And input must become output. And output can also be decrypted, can also be decrypted to be the input. This is semantic. The syntax is how we are going to change the input into the output. So the syntax is basically the rules. For example, in this case, the ciphertext is equal to the plain text position plus k. But the rule can be anything. And then we have the synchronization. For the synchronization, we need to know the timing, how the encoder and the decryptor, or the sender and the receiver respond to each other. So who create first and who encrypt first and who decrypt later, for example. 1 second, please. Okay. So this is about cryptographic algorithm. But in terms of syntax, there are several types of rules. One of the rules is that we have the encoder and the decoder sharing the same secret and the rule. And in this case, the rule always include the method and the secret. The secret is k, and in this case equals to 3. Both of them have this secret. And then the secret can be just one secret or multiple secrets. Normally, or in convention, what we normally use is that we only use one key for basic encryption, but we use two keys for complex encryption. So for simple encryption, we use one key, and for complex encryption, we use two keys. But in fact, you can use as many keys as you like, but in general, we separate this type of rule or cryptographic rules into two types. One, the sender and the receiver, or the encoder and the decoder share the same key, and that is called symmetric key cryptography. But if the sender and the receiver do not share the same key. Then we call this asymmetric key cryptography. But for asymmetric key cryptography, the encoding key and the decoding key are usually related. We will talk about that later. And finally, there's a special type of cryptographic algorithms that we can encode, but then we cannot decode it at all. There is no way to reverse the process. That is called the hash function. Let me talk a little bit about the hash function. A hash function is a function that we encode our plaintext into ciphertext, but the reverse process is impossible. For example, I have a set of input, which is or consists of number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I can hash it. This is the input. And the output can be letter A, B, C, X, Y, Z. This is the set of output. What you can notice is that the input has to be mapped to the output. But the set of outputs contain less member than the input. So we say n of the output is less than n of the input. This is the basic requirements for a hash function. Why? Because in this case, if every numbers or if every input can be mapped to an output, there will definitely be some input that maps to the same output. And usually, this mapping will always end up in a messy process like this. So, in this example, let's say that I want to send number such as 1, 2, 3. I want to send 3 numbers, 1, 2, and 3. When we actually encrypt it using the hash function, what do I get? even though this rule is known, even though this rule is known to anyone, this is going to be encrypted into letter A, C, and then X. Now we know that this rule is very well known. But if we have the output ACX can be converted back to 1, 2, 3, even though this mapping is known to everyone? The answer is no. Why? Because if you take a look at this mapping, A can be reversed back to number 1 or number 6. And C can be reversed back to number 5 and number 8. Oops, sorry. Should be number 2 as well. Sorry. And then X can be reversed back to number 3. This is known. Lucky. Given these possibilities, there is no indication or there is no tips or hints or rules saying that A can be reverted back to 1, 2, 3, as we said. These multiple possibility creates the impossible condition to convert ACX back into 1, 2, 3. This process is called hashing. So in this case, why is hashing useful? Hashing is useful because we can send number 1, 2, 3. Let's say that our this is the first use case. We use it in password, username and password. So we send letter 1, 2, 3, and then we can say that 1, 2, 3 is our password. When we send this password, let's say we have a user and we have a system. The user will send password to the system. If we send it as plain text, someone in between can hijack it. So we cannot send as plain text. So the option of using plain text is not possible. What about symmetric key? For symmetric key cryptography, both user and the system must hold this symmetric key K. However, if we have 1,000 users, everyone will share the symmetric key, the same key. Remember, there is no such thing as a non-reversible symmetric key cryptography and asymmetric key cryptography, except the hash function. So, if one of 1,000 users can find out what this key is, or by definition, for symmetric key cryptography, everyone shares the same key. This means that if I know this secret, I can basically decrypt your password. So, this is not a good option. Because anyone can decrypt the password of everyone else. If I can steal the encrypted message that is sent between the user and the system. What about asymmetric key? As you know, for asymmetric key, the encryption key and the decryption key are related somehow. So if someone find out about a key, then he should be able to find out the other key as well, given that he knows the rule. And also, the system has to remember so many keys. This is not appropriate. And then finally, we have the hash function. How does this work? For hashing, we don't use the key at all. We only use the rule, the mapping, like what you see on the left. And in this case, instead of sending this number 1, 2, 3, we actually send ACX, and then the system receives ACX. How does the system know that this password and the user match? The system was designed cleverly in the fact that the user, say user 1, the system will store user 1 against his password 1, 2, 3 as well. But in fact, when you set up the password, the server do not actually install 1, 2, 3. It performs the same hash function. And this hash function will create ACX. It will store only ACX. So if someone sent this password 1, 2, 3, it will send this person will only send ACX, and the system will only store ACX, and the system encrypt ACX using symmetric key cryptography to become maybe +1, maybe using K equal to 1, using Caesar cipher, for example, as for basic example, it will store instead B, D, Y. Given that this secret K equal to 1 is only known to the system. So when the user sends ACX, the system either convert ACX using the Caesar cipher rule to become BDY or decrypt BDY and then compare against ACX. So if no one knows about this K and no one knows 1, 2, 3, even though that person can steal this number or can steal this ciphertext ACX, the person will have no way of knowing the actual password. And this is what the system would do in checking the user against the password. So this is the basic standard practice on how user and password are matched. This process is used in authentication function. But there are some other methods, there are some other complexity that can be added in to make the password safer. But today, we have quantum computers. This reverse of the process can be incorporated into a trial and error technique. A person, even though or a malicious person, can basically reverse this ciphertext ACX. Someone can decode this into these different possibilities. How many possibilities? This is 2, this is 3, this is 1. So 1 can pair with 2, 1 can pair with 5, 1 can pair with 8, and 3. And then we can have 6 pair with 2, 6 pair with 5, and 6 pair with 8, and 3. So there could be 2 multiplied by 3 multiplied by 1 equal to 6 possibilities. So this means that if we have a powerful computer that can test all these 6 possibilities, then that person can enter the system by using trial and error. So this means that even though hash function is good, it does not completely protect the discovery of the original inputs, because if we can use trial and errors, we can use a powerful parallel machine or a quantum computer to basically reverse the process using trial and errors. So we talked about the symmetric key cryptography and the hash function. The benefits of cryptography is confidentiality. The message that we send, we can send it in secret. That's confidentiality. Non-repudiation. Cryptography, if used correctly, only the person who holds the key can be limited, and in this case, anyone who uses this secret can be identified. Integrity. If someone modifies the message during transit, the message cannot or have a high chance of not being able to decrypt it at all, or can be decrypted, but the message is not human readable. So the integrity can be broken if we use a cryptographic algorithm correctly and cleverly. Adaptability. Cryptographic algorithms, we can use it in different scenarios. A good example is username and password, just like what I said earlier, or even symmetric or asymmetric key cryptography. When we have the plain text, we can encrypt it using some secret key, can be K, or can be K1, K2, or whatever. I call this set K. Consider secret K. And this K is a set of keys. And then we will receive the ciphertext. As I said, there is probably not even one key that we use. We can use multiple keys, but another key can be dynamic. In this case, I send the plain text, and then I send the date, and then encrypt it with K. Then, if someone know K, but not know the date or seconds or some information that is extra from this secret, we call this the seed. Oops, what did I do? The seed is normally dates or seconds. Seconds since uh, maybe since the time that the first computer was created or something. This is well known. The dates can be well known, but you can add some extra information. Can be anything. So you encrypt both the plain text and the seed together to become the ciphertext. If someone know the key, but if he doesn't know the seed, or if the seed can be changed very often, then the person won't be able to decrypt this message successfully. And this is called adaptability. Interoperability. Since cryptographic algorithms allow confidential communication or secret communication. The communication is secure, and different systems can work with or can cooperate or interoperate with other systems through secure connection with a peace of mind. And finally, cryptographic algorithm can be used in authentication system. Like what I said earlier. Okay. There are several others similar key cryptography. This one is called Virginia cipher. In this case, the Virginia cipher introduced confusion into the system. And in this case, the keyword is not just one letter. It is several letters or several keys. In this case, the key consists of 5 elements. LEMON. The position of LEMON I use in this case, the plain text is attacked at dawn. But the key consists of 5 elements. L, E, M, O, N. When we actually encode it, we perform P plus K, but in this case, K have different values. And then it will wrap around to be used for encryption again and again and again. So anyone who uses only one single key will not be able to decrypt this message. He has to know all these 5 keys. This creates more difficulties and complexity to this encryption algorithm. Another method is to actually create a table, a two-dimensional table. We can send the message. The code is broken. Read in this direction. And as you can see, if we put this into a block, anything inside this block will be sent, but we don't send it along each row. We send it one column at a time. We can do this. Or before we actually send, we can actually combine this with the Caesar cipher or the Virginia cipher to cheat the characters first, and then we can send this later. In this example, we also sent the least, the column that contains the least value of the key first. So we send A, is EIK, and then we send what column next? The I column. And then we send the L column. Is it? No, the R column. And then we send the T column. And then we send the L column. So we can actually rearrange the order of the column that we want to send as well. So you can see that there are several techniques that we can use to encrypt a message. Okay, so I assign homework one last time. So this finished the review, and also I provide extra information. Let's take about 10 minutes break. We will come back to talk about the next section. All right. Let's continue. So you have seen some techniques using symmetric key cryptography. So the techniques, the first technique is to use the key. So one, we use the key. This is the secret component. The second one, it is the rule or the method. And the method can be simple arithmetics. Or this is an example of Caesar cipher. We can do plus, minus, multiply, take log, or whatever that is related to mathematics. The second method is to use multiple keys, like the Virginia cipher that we talked about. So keys in this case, we say keys. 1 second. Mm. Okay, I apologize. For the rules and method, not only mathematics, but what we have seen is that we can use multiple keys, and also we can use a technique such as the tabulation techniques, where we send one column at a time. We also have another technique called shifting. For example, this is very similar to tabulation. If we want to send the word hello, instead of sending the word hello, we shift it by one position. We will have, in this case, E, E, O, and H. When we send this. This looks like human, this looks like ciphertext. It is a text that human cannot read easily. So this is called shifting. This is shifting by one position. This is similar to the mathematics method of the Caesar cipher. So, and not only that, we have several other techniques that can basically create confusion, difficulties, and headaches for a person who want to decipher or to decrypt the message. Since there are so many types of so many types of encryption and decryption, and this depends on the encoder and the receiver or the decoder. So when we actually want to communicate with someone who we don't know before, or if we want to have um, a secure communication with another system, then before we actually communicate, you have two persons. This is, let's say, this is Alice, and then we have another person, the Bob. If Alice and Bob have never known each other before, for example, you're communicating with a server, then what you would do is that A and B will communicate with each other, and then this communication will be in secret, and they will talk to each other. This is called challenge or initialized communication. This challenge process will allow A and B to find out that you are really a legitimate user or a good computer system. This is complex, but um, I need to talk about it so that you know that between A and B, they may have some kind of ways to communicate. Usually, this involves the process of asymmetric key cryptography. And hashing, or sometimes even symmetric key cryptography. So, for example, first we use the secret uh, we use the secret K1 to first communicate with each other. But in the case that we don't know each other, we cannot use symmetric key and asymmetric key. We must use a standard. Then, after the standard is established, A and B will challenge each other and find out whether you are a legitimate user or a computer. After that, a key K will be generated. Once key K is generated, then after this, there will be encrypted or secure communication. So Please remember that in the real world, the value k has to have somehow be distributed to the sender and the receiver. And this process is called the challenge process, or in standard terms, this is called the key exchange process. And then once the key exchange process is created, then we have secure communication. The secure communication can be using a different method or the same method as the challenge or whatever. You can be very creative in doing this. One of the standard is called Data Encryption Standard, or DES. This method is created to create a very difficult symmetric key cryptographic algorithm. So the way that it works is that, one, you start with a plain text, and this is 64 bits, so it is quite long. And then you have the key. The key is also 64 bits. You see that it is quite long as well. And then you perform some kind of permutation. Permutation means you swap things around. So in addition to this, you can have permutation. So instead of hello to become ELLOH, you can do permutation. You can say LOLEH. So you basically permute it, or you switch the position in a certain way. So you create a permutation of this. Then you take the text to perform permutation. And then you split the 64-bit permuted word into two parts. Here, 64-bit on the right-hand side, the 64-bit key are first permuted as well, and select to use only 56 bits. Here, we split it into 32 bits and 32 bits, and then we encrypt it using some algorithm, either using mathematics, arithmetic, tabulation, or shifting. So each part are being encrypted, and then put them back together. And then you have the key of 66 bits. Then you perform a shift depending on the value of the shift position you want to do. Then you send this 56 bit, permuted it in a certain way, and then select only 48 bits to become the key, so that each part of this plain text, of this permuted plain text, the left part and the right part, can be encrypted using this 48-bit key. So you see that the method is complex. And once you get the result, you then have the result for round number 1. For round number 2, starting from this element, just shift it one more time, and then you permute it, and you select only 48 bits. The result from round number 1 will then be encrypted using the key you get from round number 2. This process continues on and on and on for 16 rounds. And finally, you will have the final permutation. you can see that the encryption process happens many times. This creates complexity, confusion, and the amount of time trying to decode this message. So, all in all, in the past, maybe in the past 20, 30 years ago, this method was considered very difficult to decrypt. But don't forget that the technology advanced every day. The chip become faster every day. So this standard encryption method can now be broken using try and error and also reverse engineering. This can be done in a matter of days, not months, not years. So, and some computers today can even break this in hours or minutes. So, this method, even though it looks good, but it is not as good as the technology advancement. Not only that, so to make it even more difficult, they perform the previous process for DES or data encryption standard. But this time, instead of using only 16 rounds or one time of this, they will do this for 3 more times to increase the complexity, difficulty, and confusion. And then instead of using one single key, we will use 3 keys. So the methods become even more difficult. But there are still some computers today that can start breaking this method already. Another method is called AES. AES stands for Advanced Encryption Standard. So with DES, if one can crack DES, triple DES doesn't matter, right? So we need to come up with a different method called AES. With AES, the plain text will be shifted, mix the columns like tabulation, add some internal keys, substitution of some characters. So these are the method for round number 1. Round number 2, to do things that are a little bit different. And the key itself are separated into key number 1, key number 2, and key number 3. Or key 0, 1, and 2. So you can see that this is the creation of these keys. And since we have all these keys, and then we perform this conversion from plain text, then we can start making we can start making the encryption, and then we get the ciphertext. And according to the study, this method needs to use the key of at least 128 bits, but recommendation is 256 bits. And if you perform this, it will be quite more difficult to solve than the DS and the triple DS. Okay, so we finished talking about the symmetric key cryptography and also the hashing algorithm or the hashing function. Oh, by the way, hashing function also have a standard that is very difficult to create a hash, and that is called SHA, stand for Standard Hashing Algorithm. I won't forget it because this is not a cryptographic course, but if you're interested, you can find this out. And this is standard hashing algorithm. If I remember correctly, we have SHA1 means version 1, and we have SHA2 means version 2. I'm not sure if there is SHA3, but according to my understanding, for hashing function, SHA2 is quite powerful already. Now we're going to talk about asymmetric key cryptography. And ISA algorithm is one of the most famous algorithms using asymmetric key cryptography. Okay, I'm going to take 5 minutes break, and we will come back to talk about this. Okay, let's take a break. All right, let's continue. In the next section, we're going to talk about asymmetric key cryptography. And for this cryptographic method, I will show you some example and some basic concept. But the real implementation is quite difficult. But I will show you the core principle on how this works. So, the principle is that assume that the principle is that for ISA algorithm, the word RSA are from the name of three persons. So they combine this together to become ISA. And the way that it works is that, just like what I said earlier, we can use multiple keys. But for asymmetric key cryptography, the encoder use one key called encoding key. And the decoder or the recipient use another key called the decryption key. So we have encryption key and the decryption key. This is the encryption key. And the encryption key and the decryption key are related somehow. Let me show you in this example. And this method is genius. That's why this method is still in use even today. Okay, so let's say that we want to first create a key. The key are defined to be two prime numbers, P and Q. Remember, we talked about an algorithm to find a prime number before, and it was not easy. But let's say that this is a toy example. So P in this case is 11 and Q is 13, two large prime numbers. In the real world implementation, this must be two very large prime numbers. Why? Because it is very difficult to find a factor. Then we will calculate n, where n is p multiplied by q. In this case, n is 143. And then we come up with, this is called Bn. And this function takes P and Q, each decrement by 1. So it is P minus 1 multiplied by Q minus 1. We get this as 11 minus 1 multiplied by 13 minus 1, and that is 120. Once we have n and phi n, then we will create something called a public exponent. Actually, we call this an encryption exponent. So this is called encryption exponent. this exponent is chosen arbitrarily, means that you can select any E. So in this case, we choose E equal to 17 with a constraint that E must be less than phi n, and phi n must not be divisible by E. So usually E is taken to be a prime number, a very large prime number that is less than phi n, another prime number. So we will let E equal to 17. We test it and find that the GCD, or the greatest common divider, between 17 and 120 is 1. So this checks. And then we create the decryption exponent. As what I said earlier, the decryption exponent has to somehow be related to E. So we come up with this constraint. D has to be chosen just that D multiplied by E and mod of this phi must be equal to 1. So in other words, I can say that D dot E mod Phi must be equal to 1. So how can we do that? We can use trial and errors or the brute force attack, change the value of D for several times, and then we found that D is equal to 113. So we try D equal to 1, 2, 3, 4, 5, so on and so forth, until we get D equal to 113. Because this is the value that will make 113 multiplied by 17, and then mod with phi n. And we get this, mod this, which is what? Which is 1. Because 1921 mod 120 is just 1. Because 1921 is equal to 120 multiplied by 16 plus 1. And once we have this, we will say that E is our key number 1, or part of key number 1. And key number 1, or encryption key, is equal to the two number N and E. And the decryption is N and D. And we have two keys, encryption key and the decryption key. So assume that we have the key already. So the first key is N, which is 143. So we send 143 with number 17 to Bob, to who sent this. Let's say Bob sent this. So Bob sent this. The first key is always referred to as the public key, because Bob can share this key with anyone in this world. Oh, it is not secure, isn't it right? You're not supposed to share the key. The answer is yes, you're not supposed to share the key. But the rule itself is so damn difficult because if you involve a very large prime number, like 128 bits, for example, then you have to spend a very long time to decrypt this or to find the information about this key. And then once we have this public key, the decryption key, we call it the private key, is 113. Actually, we can swap these two numbers, but for the story that I have arranged so far, the first key that we found is the public key. So let's take a look at how we can encrypt and decrypt this using asymmetric key cryptography. Let's say that Bob wants to send a message to a list. Remember, if Bob does not know a list before, a key exchange process must happen. Then we need to exchange the key. But this key is so important. You should not transmit this key over a non-secure channel. So what should we do? We say that Bob and Alice will use ISA cryptography. So Bob will generate two keys. One, the public key, and two, the private key. Since both B and A have to work with each other, but they don't know each other before. So Bob will provide A with a key that I want to use. So KE will be moved to the right hand side. What does this mean? This means that B can allow A to have its encoding key or the public key. The reason why we call this public key is obvious. B can send this information to many people. Okay. Okay, D is our private key. And in this case, let's say that oh, sorry, I was wrong. Bob can send this public key to many people. This is another key. This is also Bob's public key. What I want to demonstrate here is that anyone in this world can have Bob's public key. But no one would know about Bob's private key. So, in this case, Alice have Bob's public key. And also, Charles or C also have Bob's public key, but not the private key. In this situation, Alice want to send a message to Bob. So Alice use public key NE to encrypt the message. Why? Because in order for Alice to send a message to Bob, Alice must ensure that only Bob should be able to open this letter to read. Charles, as the C person, Charles should not be able to read this encrypted message. Even though C have Bob's public key, C cannot use Bob's public key to decrypt this ciphertext from a list using Bob's public key. Confused? Again, a list wants only Bob to be able to read this message, not Charles. So this means that a list must use one of the key of Bob. A list will decide to use Bob's one of the Bob's key, and we call this public key. The public or anyone can know Bob's public key, and Bob and Bob doesn't care. This is called the public key. If a list encrypt using Bob's public key, only the person who has the key pair, which is Bob's private key. And if anyone has Bob's private key, he can read this. But if anyone has this public key, the person cannot read this. Okay, so in this case, Alice wants to send a number. In this case, it is M equal to 88. And then, since Alice has Bob's public key, it is 143 and 17. Then the ciphertext will be created using the following formula. C equal to M power with E yeah. C equal to M to the power of E mod N, so that the result is wrapped around. And we get this. And I perform this on the calculator, we got 121. This process may be super difficult because in the past, but today this is doable. So this is the method. And then number 88 is now become the ciphertext with the value of 121. So Bob received the ciphertext C equal to 121 to decrypt it using the same process but in reverse. So we will have we can decrypt using this. You see that this yeah, this we have. So for encryption we have 1 second. This is the ciphertext C. And we take the ciphertext, we then perform ciphertext to the power of D and then mod with N. Here we take the private key D. D is our private key. And we perform this formula. So this is what we did. Where M prime represent the original plaintext that we decrypted. This method, even though it is not 100%, but it has a very good chance that no one should be able to crack. And once you perform this formula, then this will become 121 to the power of 113. What do you think? This is a very large number. And the final outcome is here, 88, which match with the original. Okay. Um, are there any questions so far? The method is very simple. You come up with P and Q. With P and Q, let me write down here. So you first define P and Q. Okay. So the process of finding P and Q is already difficult enough because we want to use a very large prime number. And then once we have P and Q, we generate N equal to P multiplied by Q. But Pn equal to this. Oops. Wrong. And then we say that we will choose a number, E, given that E must be less than this. Now, once we find E, then we find D. And D must be a value that here is a value that will make what? Will make E and D here. And then mod of n to be equal to what? E is known, n is known. So we can create this. And once we have D, we have E, then we pack them together and say that the key is N and follow with E. This is key number 1. And then we have key number 2, which is N and D. Is it? Yeah. So we have 2 keys, key number 1 and key number 2. As you can see, if we can apply this rule and we can perform encoding techniques using encoding rule as C equal to M to the power E mod D. And in this case, you have this, the original message to be estimated from the decoding back into here. And this is sorry, C to the power D. And then and then we solve for D because we know mod N and we know C. We also have D. So by doing that, you get the 2 keys. The reason why we call key number 1, the encryption key, as the public key is because we want to make sure that anyone can encrypt information to Bob, and Bob is the only one who can read this. That's why this is called asymmetric key cryptography. No one has private key. That's why it gets the name private. no one can find this decryption key because by human definition, the decryption key is kept very securely. However, or vice versa, since anyone can use Bob's public key to encrypt information and only Bob can read it. On the opposite side, anyone should be able to know that this is Bob encrypting this information. By doing this, if Bob wants to verify that he is actually himself, given that everyone has the public key of Bob's beforehand. So Bob will sign the message, but this time he will use the private key to basically encode the plain text. The ciphertext can be read by anyone who has the pair of this key, which is the public key. So anyone who can decode this message should be able to find, should be able to guarantee that it must be Bob writing this message, because no one can create this encrypted message that can be decrypted using Bob's public key, other than the person who has the private key. And by definition, only one person can have this private key. So this means that if someone used the private key to encrypt the message, that person must be Bob himself. Okay? So this is the essence of asymmetric key cryptography based on ISA algorithm. The mathematics may be difficult, but the hardware has become much, much better. So, so you have to be very careful in using cryptography. In this case, if we have, in practice, when we use ISA algorithm, we have a document. The document, we will create a metadata. For example, you can count the number of words in this document, for example. So we have something called the checksum. Then this checksum is hashed and then encrypted using Bob's using Bob's private key. The information of the document and the encrypted hash of this document, or actually the hash of the checksum of this document, is attached along with the document when Bob sends this to Alice. Alice take this message, take out the header part which contain extra information about this encrypted hash of the checksum. And then once Alice receive this message, at least take a look at the header, and then take a look at the document. At least use the same algorithm to create the checksum. Okay, the checksum of this document. If there is no alteration or no modification of this document, the checksum between the two must be the same. But currently, Alice have no idea what is the value of this checksum. So Alice take this encrypted hash of the checksum. The person will reverse the process using Bob's public key, because anyone can have Bob's public key. So Alice take Bob's public key and then decrypt this information. And if the decrypted ciphertext here, the output should be decrypted hypertext. Oh, I apologize. If Alice use Bob's public key, Alice should be able to decode this and get the hash of the checksum. Alice take the document, calculate the checksum, and then hash it, and find out whether the plain text that has been yeah. This is the the real info, which is the real hash of the checksum. And this is the decoded info. And then you compare them against each other. If they're the same, here, this is the comparison part. The hash of the information is done here, and then the decryption that is sent by Bob also arrive here, and then we compare the two hash functions. The result of these hash functions. If they're the same, it means that it must be Bob who wrote this message. Otherwise, then it is not Bob who read this message. Oh, sorry, who write this message. And that's it. This is called ISA digital signature. So we have ISA encryption and ISA digital signature. We use the same process, but the reason why we call this differently is that for digital signature, only Bob can read, only Bob can write this message and send to Alice. That makes that makes the encrypted information using Bob's only key, and this key is kept private as digital signature, because it's only Bob who can be identified using this. And this provide, ISA digital signature and ISA private key cryptography provide a foundation of several other standards that we have in cryptography. But don't forget, ISA is still in use today. It is very difficult to find a number that or to find the value of um, to find the key. Basically, it is very difficult to find the key, and it is very difficult to um, to to do try and error method, trying with different keys. Okay. Due to my health, I haven't finished explaining about project number 2 yet, but I will assign this later today or tomorrow. Okay, we will take about 5 minutes break, and then we will talk about the next topic, which is called AI algorithm. I haven't uploaded it yet, but during the break, I will upload it to my courses. So for this time, please take a break, and then we will talk about the the AI algorithm, a simple one. Okay, let's continue. So, in the last section, we're going to talk about AI algorithms. So, what is AI? AI means artificial intelligence, which is a machine-based system that can basically mimic human-defined operation. Usually, AI systems are um, are separated into two types. One, a predefined rule system, and another one is called the autonomous system. But the way that AI system operates is that AI system can basically replace human by performing human tasks. Simple as that. So artificial intelligence is basically a system that can work like human, but they can do a better job, just like what we created computer for in the first place. We want computer to do things that we can do, so that we can do some other things that is better. So, by definition, this is provided by NIST, National Institute of Science and Technology of the United States. The key components of AI consist of several things. There are several paths or several types of AI, like what I said earlier. Today, AI consists of machine learning, deep learning, neural networks, natural language processing, computer vision, and cognitive computing. So these are modern AI systems. Machine learning is a subtopic of AI that focus on algorithms that can learn from uh, from data pattern. So if you provide some relationship between the input and the output, so for some reason there is an input and an output, then the AI system can try to learn the rules that convert the input to the output. In the previous session, we talked about cryptographic algorithm. We can have the input and we can encrypt it into the output. Machine learning system can actually learn, just look at the input and the output. You don't need to provide the rules, but for machine learning, the system should be able to define the rule or find out what the rule is, and also the parameters such as the secret key or K that will make the input to become the output. That is called machine learning. And if you're interested, you can register for machine learning, which will be offered in the next semester. The machine learning, machine learning have to predict the rule. and also the parameters that the rule use, and the reason why we call this machine learning, because the machine will try to learn what is the rule and what is the secret, what is the parameters used in for this rule to make the input become the output. The rule today, just like human, if we want to know the rule, we should at least have some example or some knowledge about rules that are normally used or rules that are common. We call those rules as model. The model can be many things. Like what I said earlier in the previous session, the model can be based on mathematics. The model can be based on the shifting. The model can be based on permutation. The model can be based on tabulation, so on and so forth. But for machine learning, this is the model for cryptography. We call this cryptographic model. But for machine learning, there are other set of models to learn this relationship. And this model consists of regression. We also have classification. We also have clustering. And for regression, there are many subtypes of regression, such as linear regression, multivariate regression, multiple regression, for example. For classification, there are many other types, such as logistic regression, decision tree, random forest, gradient boosting, also neural networks. For clustering, we have k-means, we have some other techniques. I forgot the name, but there are several submodels in here. All of these are called machine learning model. The machine learning models, sometimes these models are basically the framework or the basic rules. The model itself that I explained here do not include the parameters used to transform input to the output. The actual specific model will include the parameters that are used for each different model. The model without the parameters are called the foundation model. And the foundation model, once you come up with the specific values of those parameters, those will become the machine learning model specific to this dataset or specific to this training data. So this is the general overview of machine learning. Neural networks is a foundation model of machine learning that allows inputs to go through different linear operation and then finally produce the output. Amazingly, these complex linear operations in multiple layers that can convert from input to the output. Each node, each linear operation, or each math operation is called a neuron. For basic neural networks, we have a small number of neurons. But as we increase more number of neurons into different layers, this is one layer, this is another layer, so on and so forth, this will be called deep learning. So deep learning is basically a large amount of layers in the neural networks. And then there are some other several methods in the neural networks that not only you can go forward in the computation, you can also wrap things around to create some kind of memory or to create something that you can focus on some of the nodes called attention. Those things create several submodels for deep learning. You will learn about this in machine learning class next semester. And finally, one of the application of machine learning is computer vision. If we apply deep learning with images or videos, we call that computer vision because it is the data that we can visualize. Another term is called reinforcement learning. Machine learning model learn usually by trial and errors. You learn from different patterns, and then you try to fit a foundation model to a pattern and determine whether this foundation model fit or not fit using different parameters. However, there is a different type of learning, just like how you learn from mistakes. For example, when you were young, you try this, you try that. If you hurt yourself, then you get penalized. You try to forget that thing. But if you do something good, even though it is not the best, you start to remember and try to improve it over time. That is called reinforcement learning. You try to improve what you learn. I won't go into much more details, but you can learn more about this in the machine learning course. Cognitive computing is a model, a machine learning model that can closely simulate human cognition. Cognition means to realize what is what. Cognition is the big topic in artificial intelligence. Cognition and consciousness are very abstract. To be conscious or to have cognition means that the machine has to understand. The word understand is very subjective. How do you define the word understand? And if someone can understand something, then the person must be able to do something else that does not require training data. At that level, a computer can create new things without requiring past information. Today, machine learning, deep learning, all of the AI methods that we use today cannot generate new things. It can only generate things that it has seen before. It needs a large amount of information to learn many, many things. But to create new things like new arts, new music, new type of music, new type of pattern, new type of model, with the current technology, without cognitive computing, we can't do that. Machine can't do that. Another type of model, another type of AI system is called generative AI. Generative AI is a system that goes one step beyond machine learning. For machine learning, you learn how the input can be converted to the output. But for generative AI, you have, if you are provided an example of the input, and then you give it some more information of the input, then it can basically use the rules that it learned to generate the output that correspond to the input. This is called generative AI. So once you know the rule, once you know the model, next time when you provide an input, you can generate an output. This is called generative AI. Today, generative AI are being used widely. It is widely popular due to the support of another type of AI called natural language processing. Natural language processing aims to provide a model for a computer to analyze how humans react or how humans write sentences and also react to questions. So we can have a machine learning model that read a textbook. When you say this word, this is the next word that you want to say. So they can make this relationship. Or when someone asks this type of question, when someone sends this sentence, it can learn 1,000 examples of similar questions. And then it can generate an answer based on what it learns from the book or from human conversation records. That's create a generative AI system that are popular today, such as ChatGPT and Google Gemini. You will learn more about this in the next semester in machine learning class. But coming back to the basic, AI algorithms tend to use human model or human method to solve questions. And then when you provide a new input, it can give you the answer. You have learned several algorithms that mimic how human thinks. You learn the shortest path algorithm. You learn spam filtering algorithms. You learn game playing algorithms. You learn traveling salesman's algorithms. And today, I will teach you a minimax algorithm that I use to play games against another player. I want to introduce this game called the tic-tac-toe. In Thai, this is called OX game, but it is commonly known as the tic-tac-toe. The tic-tac-toe game created since the 13th century before Christ. It's 1300 BC, starting from since Egyptian time. And the game plays like this. You place X and O in a 3x3 matrix. And this game will win if anyone or any player, X or O, can have 3 consecutive positions, either in vertical or horizontal or diagonal. So there are several ways to win. So an action of each player is to try to find a way to win by placing X or O in this pattern. And at the same time, once a player places its marks, it prevents another player to play. So in this case, player 1 and player 2, or player X and player O, will compete with each other to try to be in the winning position. To have a winning position, assume that currently player 1 or Alice are given the situation that he has to place his mark first. This is a turn-based game or a basic board game. So in this case, if Alice places his position or her position in this cell 0, 0, then Bob can place his mark as O in any of these positions. Since there are 9 positions, so Bob will have 8 positions to play. So, given Bob's or player 2's ability to play, in this example, there should be 8 possible solutions for Bob. For each above solutions, player 1 will have other solutions to play and try to win it. So, if in this case, Bob place the first move in the center, this one. Then Alice or player 1 will have a very high chance to win if he plays his mark X in this position. He will definitely win because no matter what, no matter what player 2 or Bob will play next, no matter which position to for Bob to play, Alice will win anyway. Okay, then for human strategy, how can we play that? We will assume that the strategy is as follows. Player 1 will try to maximize, and player 1 will try to think that player 2 will try to maximize his advantage as well. In the view of player 1, when it is player 2's turn, player 1 will try to minimize his gain when player 2 plays. This is basic. So let's take a look. Assume that currently the board is in this position. So this is this is what is presented to Alice at the moment, or X at the moment. X has 3 positions to play. 1 position, this is called the left position, or center position, or the right position. If this is 0, position, this will be position 2, 0. This is position 2, 1. And this is position 2, 2. Currently, let's think along. I don't know, or Alice doesn't know which position to do. So Alice will think, if I start from position 2, 0 to the left, then Bob would win if he placed his mark right here. This is the position that I think Bob will play. My score, I say that if I win, I get 10. If I lose, I minus 10. So in this case, my score will be minus 10. Because I know that Bob will do this, definitely. Otherwise, Bob will do this. Will place his O at position 2, 2. And then I can place this. Place my X right here. And the result will be in a draw. What does this mean? If I play this, I result in a draw. It means that I will definitely take this because I want to maximize my profit when it is my turn. Then, going back, my turn profit is still 0. In this case, when I go back up. But when I compare this at the same level with Bob's turn, I need to know that I have to minimize my profit. So 0 and minus 10 will produce minus 10 going to the top. Let's leave it like that. It means that if I take the left position, if I take position 2, 0, I will lose anyway. I will most likely lose. Or I can draw. This doesn't seem a good option. But if I take position 2, 1, If I take position 2-1, Bob will have two other options to take. One at position 2-0, the other one at position 2-2. If Bob takes position 2-0, I can take this position 2-2 to win. This means that I can maximize my profit to +10. And it is now waiting for Bob's turn. But if I take the route on the right-hand side, then here, Bob will take 2-2. I will have only one place to take, which is 2-0. Then my profit is 0 because it's enough in the draw. To maximize my profit, I take this 0. But definitely, Bob knows about my position, or should know about my thinking. Bob will try to minimize my profit. Bob will send 0 up top. So if I take this position 2-1, I will definitely, or most likely, will get 0 because of Bob's decision. But if I take position 2-2, I know that I will win right away, and Bob will have no chance to make a decision. This will be +10. And then, since this is my turn, since currently this is my turn, I should maximize my profit, right? So I will definitely take this position. I should put my my piece, or I should mark my X at position 2-2 to win this game. So to go back to recap this, when it is my turn, I want to send the maximum score up top to another level, to the upper level. But if it is my opponent's turn, then I will try to be pessimistic. I will try to minimize my score position. And then when it is my turn again, I will try to maximize my score or my advantage. In this case, this is called Minimax algorithm. With this Minimax algorithm, the maximum and the minimum are being considered back and forth, back and forth. With this, we can come up with this algorithm. I explained this to you already, so you can read this. So we say that in order to play this game, first we will determine whose turn is it. It is divided here. Whose turn is it? It's maximizing player. If it is, then I will try to get all the score from the previous depth, and then I will try to maximize the value and return the maximum value to the upper layer. And then given the present layer, which is the board and the depth, if I am not maximizing, I'm thinking in the aspect or in the thinking for my opponent. My opponent will try to minimize my score. So again, I will go to the lower layer, grabs all the scores from the lower layer, just like what I just explained to you, and then deliver the minimum score as the base value for the opponent's turn. But if I cannot go down anymore, if I'm at the lowest depth, I will return the score, which is the winning position. If I win, I get +10. If I lose, I do -10. To know whether I am at the terminal state, I will count how many cells left in the board. If it is 0, then this is the end of the game. Okay? And also, there might be possibilities that I want to maximize my chance of winning. I want to win fast, and even though I don't win, I want to lose. I want to lose later by creating as much delay as possible. So this means that for each maximum score that I have, I want to win very early, and I want to penalize the winning score with a debt. The less debt that I have, I want to win first. But if the winning path is from a very long debt, a very long levels, then I want to penalize that score. I don't want to use that score. So every time when we want to submit the score, we want to penalize the debt to the winning. But if I'm losing, I want to penalize the losing by adding the debt because I want to increase the length, like what we see here. Even though I don't win, but there might be a chance that I will win if Bob plays his position at my, if he plays it at my advantage, so I can still win. But I would still choose the right position because it allows me to win faster. So this is how I use the debt to affect my winning score or losing score. By doing this, you can implement this using a toy example. Coming up with this, I copy the code from here. So you can first create the board. You define availability using this symbol. Your mark as X and O are provided here. To play this game, you call find base move for this current move. And then the program will call the base move function. The base move function here will basically take the board and then for minimax function, just like what I explained to you earlier. What is the board? What is the debt? And then, am I playing or not? If I'm not playing, then we call this minimax function. If I'm playing, then you continue with the minimax function with the player. And what is the minimax function? The minimax function first will try to evaluate the current value of the board by calling by checking first whether I am at the whether I have any position left, and if it is, then the function will then consider all the debt, traverse all the cells, and then for each cell, it will try to find out the minimax value. It will return the max if it is the maximizer move. Otherwise, then if it is the minimizer's move, it will try to minimize the score that it received from depth plus 1. If it is the max, it will try to maximize the score from from depth plus 1, just like how I explained to you earlier. So you can study this code and then you can provide the score based on the maximum value and the minimum value. And finally, when you are done, you can check if there is no move left, then you will return the current score. And that's it. You can try to play this game. You should try implementing this and think about how this is implemented. And then the homework is that I give you the algorithm. Now create a game, a tic-tac-toe game that allow a human to play. To play, you can ask human to input 0001 once or what or 02 or 10. So basically, the program should be able to provide a table and then provide the current state of the table and then ask the player which position to place his to place his mark, and that's it. And try to see whether a player can beat the tic-tac-toe algorithm. I bet a player will never be able to do that, but who knows? Okay, so this is the homework. I apologize for overtime, but I would like you to work on this homework, and the final exam will be next week. I will provide it either on Saturday or Sunday. It will be take-home exam as well. All right. Thank you very much for today. I will see you again next week. Have a good weekend. Thank you very much.
Thank you, Kajan.
Thank you, Ajahn.
Thank you.
Thank you, Ajay.
Thank you. Thank you for all the hearts. Thank you.